There are a few exemptions in the National Electrical Code that allow motors to have smaller rated wires than their rated current. Rule 430.22 A. Motor protection states that overcurrent protection devices, such as fuses and circuit breakers, must protect motors from overload and short-circuit currents. If the motor has built-in overcurrent protection, such as thermal overloads, the wires supplying the motor can have a lower ampacity than the motor's rating. Rule 430.22 C. Branch circuit conductors dictates that conductors supplying a motor can have an ampacity not less than that of the motor branch circuit conductors. If the motor is started directly without a motor starter, the branch circuit conductors must have an ampacity not less than 125% of the motor's nameplate current. If the motor is started through a motor starter that provides overcurrent protection, the branch circuit conductors can have an ampacity not less than 115% of the motor's nameplate current. Rule 430.24 Motor controllers says motor controllers must protect motors from damage due to excessive temperature or voltage, and they can have lower rated conductors than the motor's rated current. For example, a motor is rated for 60 amps peak and 30 amps continuous. However, the wires on the motor itself are only 16 American wire gauge, which is rated for a maximum of 10 amps. It is likely that the motor has built-in overcurrent protection, such as thermal overloads. This protection would prevent the motor from drawing more current than the wires can handle. If the motor is started through a motor starter that provides overcurrent protection, the branch circuit conductors can have an ampacity of 115% of the motor's nameplate current, which would be 34.5 amps. This would allow the use of 16 American wire gauge wires on the branch circuit. While the National Electrical Code allows some exemptions, it is generally good practice to use wires that are rated for the maximum current draw of the motor, especially if the motor is expected to operate under heavy loads or for extended periods. Additionally, the wires and the motor itself should be considered part of the motor's internal components. They are designed to operate within the limitations of the motor's construction and are typically not intended to be replaced or oversized. To further clarify these points, let's delve deeper into the specifics of each National Electrical Code section and their implications for motor wiring. Firstly, regarding Rule 430.22 A, it's crucial to understand how built-in overcurrent protection works. This protection typically involves thermal overload relays or electronic overload devices integrated within the motor or its starter. These devices monitor the motor's temperature or current and trip the circuit if either exceeds a predetermined threshold. This threshold is set to protect the motor windings from overheating, which can lead to insulation breakdown and motor failure. Because this protection is in place and acts faster than a standard breaker in the panel would, the code permits smaller conductors to be used since it is not a standard breaker used for standard wiring. The key here is that the overcurrent protection is specifically designed to protect the motor and its internal wiring. Secondly, when considering Rule 430.22, see the distinction between starting a motor directly versus using a motor starter is significant. When a motor starts, it draws a significantly higher current, known as the inrush current or locked rotor current. This current can be several times the motor's full load current. If the motor is started directly, the branch circuit conductors must be sized to handle this high inrush current, hence the requirement of 125% of the motor's nameplate current. However, a motor starter, especially one with reduced voltage starting capabilities, can limit this inrush current. Reduced voltage starting methods such as auto-transformer starting or part winding starting gradually increase the voltage applied to the motor, thereby reducing the inrush current. Because the inrush current is limited, the branch circuit conductors can be sized smaller, based on 115% of the motor's nameplate current, assuming the starter provides overcurrent protection. Thirdly, Rule 430.24 addresses motor controllers, which are devices used to start, stop, control, and protect motors. Motor controllers often include features such as overload protection, undervoltage protection, and phase loss protection. These protection features safeguard the motor from various electrical faults and abnormal operating conditions. The conductors within the motor controller itself may be smaller than the motor's rated current because they are only carrying current for control and signaling purposes, or because they are protected by the controller's internal overcurrent devices. Now, let's apply these concepts to the specific example of a motor rated for 60 amps peak and 30 amps continuous, with 16 American wire gauge wires on the motor itself. The fact that the motor has 16 American wire gauge wires which are rated for approximately 10 amps suggests that the motor is designed with built-in overcurrent protection. The motor manufacturer has likely incorporated thermal overloads or other protective devices within the motor to prevent it from drawing excessive current that would overheat the 16 American wire gauge wires. These built-in protective devices are crucial for ensuring the motor's safety and preventing damage to the motor and the connected wiring. Furthermore, if the motor is started with a motor starter that provides overcurrent protection, the branch circuit conductors feeding the motor can be sized based on 115% of the motor's nameplate current, as per Rule 430.22. C. In this case, 115% of 30 amps is 34.5 amps, which would still allow the use of appropriately sized conductors. It's important to note that the National Electrical Code provides minimum requirements for electrical installations. While the code allows for certain exemptions and reductions in wire size, it's always a good idea to consider the specific application and operating conditions of the motor when selecting wire sizes. If the motor is expected to operate under heavy loads, experience frequent starts and stops, or be subjected to high ambient temperatures, it may be prudent to use larger conductors than the minimum required by the National Electrical Code. In addition to the National Electrical Code requirements, motor manufacturers also provide recommendations for wire sizes and overcurrent protection based on the specific characteristics of their motors. These recommendations should be carefully considered when designing and installing motor circuits. Motor manufacturers often conduct extensive testing and analysis to determine the optimal wire sizes and protection schemes for their motors, and their recommendations should be followed to ensure reliable and safe motor operation. Another important consideration is the length of the motor circuit. Voltage drop can occur in long circuits, which can affect motor performance and efficiency. To minimize voltage drop, it may be necessary to use larger conductors than would otherwise be required based on the National Electrical Code and capacity tables. Voltage drop calculations should be performed to ensure that the voltage at the motor terminals remains within acceptable limits under all operating conditions. When selecting conductors for motor circuits, it's also important to consider the type of insulation. Different types of insulation have different temperature ratings, which affect the ampacity of the conductor. Conductors with higher temperature ratings can carry more current than conductors with low temperature ratings. The appropriate insulation type should be selected based on the ambient temperature and the operating temperature of the motor circuit. Finally, it's important to remember that the National Electrical Code is a living document that is constantly updated to reflect changes in technology and industry best practices. Electrical professionals should stay up to date on the latest National Electrical Code requirements to ensure that their electrical installations are safe and compliant. The National Electrical Code is not a substitute for sound engineering judgment, and electrical professionals should always exercise caution and good judgment when designing and installing motor circuits. In summary, the National Electrical Code allows for certain exemptions in motor wiring based on factors such as built-in overcurrent protection, motor starter type, and motor controller characteristics. However, it's important to carefully consider the specific application and operating conditions of the motor when selecting wire sizes and overcurrent protection. Motor manufacturers' recommendations should also be followed to ensure reliable and safe motor operation. Always adhere to the latest National Electrical Code requirements and exercise sound engineering judgment when designing and installing motor circuits. To further illustrate these principles, let's consider a few additional scenarios. Imagine a situation where a motor is located in a high ambient temperature environment. In this case, the ampacity of the conductors feeding the motor would need to be derated to account for the increased ambient temperature. The National Electrical Code provides derating factors for different conductor insulation types and ambient temperatures. These deterring factors must be applied to the conductor ampacity to ensure that the conductors do not overheat. Alternatively, consider a scenario where a motor is subject to frequent starts and stops. In this case, the conductors feeding the motor may need to be sized larger to account for the increased thermal stress caused by the frequent starts and stops. Each start subjects the conductors to a surge of current, which can cause them to heat up. Over time, this repeated heating and cooling can degrade the conductor insulation and reduce its lifespan. Using larger conductors can help to mitigate this thermal stress and extend the life of the conductors. Furthermore, let's explore the impact of harmonic currents on motor wiring. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as variable frequency drives. These harmonic currents can cause additional heating in conductors and transformers, which can reduce their lifespan. If a motor is fed by a circuit that is subject to harmonic currents, it may be necessary to use conductors that are specifically designed to withstand harmonic currents. These conductors typically have larger neutral conductors and are designed to minimize eddy current losses. Also, it's worth noting that the National Electrical Code provides specific requirements for grounding motor circuits. Proper grounding is essential for safety and for preventing electrical shock hazards. The grounding conductor must be sized according to the National Electrical Code tables and must be properly connected to the motor frame and to the electrical service ground. Additionally, surge protection devices may be required to protect motors from voltage surges caused by lightning strikes or other electrical disturbances. Voltage surges can damage motor windings and other electrical components. Surge protection devices divert these surges to ground, protecting the motor from damage. In addition to the National Electrical Code, other standards and regulations may apply to motor installations. For example, the National Electrical Manufacturers Association (NEMA) publishes standards for motor construction and performance. These standards provide guidance on motor efficiency, torque, and other performance characteristics. Additionally, local building codes and regulations may impose additional requirements for motor installations. It's important to be aware of all applicable standards and regulations when designing and installing motor circuits. When troubleshooting motor wiring problems, it's essential to follow proper safety procedures. Always disconnect power to the motor circuit before working on the wiring. Use a multimeter to verify that the circuit is energized. Wear appropriate personal protective equipment, PPE, such as gloves and safety glasses. If you are not qualified to work on electrical equipment, contact a qualified electrician. Common motor wiring problems include loose connections, corroded terminals, and damaged insulation. These problems can cause motor malfunctions, overheating, and electrical shock hazards. Inspect the wiring for any signs of damage and repair or replace any damaged components. Tighten any loose connections and clean any corroded terminals. By understanding the National Electrical Code requirements, motor manufacturers' recommendations, and other applicable standards and regulations, electrical professionals can ensure that motor circuits are designed and installed safely and reliably. Remember to always exercise caution and good judgment when working with electrical equipment. The principles discussed can apply to any situation where the conductor appears to be smaller than the current rating would imply, such as equipment that are UL listed.